Hey there, and welcome back to the Deep Dive. Today we're embarking on a journey through the fascinating, sometimes bewildering evolution of artificial intelligence and machine learning. The very first attempts to teach machines to see, all the way to the powerful, often opaque systems shaping our world today. You've asked us to unpack a stack of incredible sources, articles, research papers, insightful books that really lay bare the foundations, the breakthroughs, and the pressing debates surrounding AI.
Exactly. And our deep dive today, it's going to trace a path that reveals not just how these technologies work, but maybe more importantly, why certain approaches gained traction and, what challenges they presented and the really profound questions they raise about our future. Think of it as a shortcut, maybe. A shortcut to understanding the currents that have brought AI to where it is today. We think you'll find some surprising facts and plenty of those aha moments along the way.
Okay, so what's our mission today? We're going to explore how early ideas like perceptrons laid the groundwork, but then kind of hit these unexpected walls. Then we'll see how the field diversified, bringing in more mathematical rigor, probabilistic models, leading us to some incredibly clever ways to handle sequential data, like speech. That's a key bit we'll unpack. And finally, we'll dive into the deep learning revolution, the core concepts underpinning these systems, and crucially, the massive societal and philosophical questions they compel us to confront. Okay, let's dig in. All right, let's rewind a bit. Way back to the very origins of AI. Before deep learning, before neural networks were, the buzzword, researchers were grappling with much simpler ideas, but still really ambitious ones, trying to mimic intelligence. And one of the earliest, most influential concepts was the perceptron, right, back in the late 50s.
Indeed. Yeah, our sources describe the core idea of perceptrons as an abstract definition of a parallel machine designed for significant computations. Basically, they were simple artificial neurons. They could learn to make decisions based on inputs. And at the time, they seemed really promising, powerful enough in function, suggestive enough in architecture, as one source puts it. There was this real hint of a future where machines could truly learn. The promise felt immense, generated a huge wave of optimism. AI felt like it was just around the corner.
It sounds like a truly exciting time, just full of these groundbreaking possibilities. But like with a lot of early tech, they pretty quickly ran into some very real limitations, didn't they? Which makes you ask, what did we learn from those initial roadblocks? How did they reshape where AI research went next?
Well, the defining moment, maybe a kind of historical pivot point, really came with Marvin Minsky and Seymour Papert's work, Perceptrons, published in 1969. That book had a profound impact. Not just for its science, but because it delivered this rigorous, formal proof of the fundamental limitations of single-layer perceptrons. It wasn't just saying these don't work well, it was a mathematical iron wall, essentially.
Right, I remember reading about that,
Uh-huh.
and it really did shift the whole direction of AI research for, well, decades. What
Yeah.
was that specific limitation they highlighted, the game changer? What exactly couldn't these early systems do?
Okay, so one of the key things they proved was that perceptrons were fundamentally unable to recognize properties like connectedness. So imagine trying to teach a machine to tell the difference between, say, a single continuous line on a grid and two separate disconnected lines. Or just telling if a simple shape, like a letter T, was one continuous piece or multiple disconnected bits. The book gave a formal proof that perceptrons just couldn't get that. It wasn't about size or inputs. It was an inherent flaw for single-layer models trying to solve problems that weren't linearly separable. And the sources really emphasize this took many months of work to prove formally. It shows the depth of their analysis.
Wow.
This wasn't a minor hurdle. It was a profound constraint on what these early networks could do, especially for anything like real-world pattern recognition.
So it wasn't just a matter of making the perceptron bigger or feeding it more data. There was like a mathematical ceiling, a boundary it just couldn't cross for certain tasks.
Exactly. And they also dug into this idea of the order of predicates. Think of a predicate as just a feature or a property that AI is trying to spot. The order is basically its mathematical complexity, detecting if one pixel is on, maybe order 1, simple. But detecting something more abstract, like parity, whether there's an even or odd number of active pixels in an image, that's a much higher order predicate. Minsky and Papert showed that for these complex predicates, like parity or symmetries, perceptrons would need impossibly huge coefficients. Basically, numbers so big it made them practically impossible to build, even if theoretically they could recognize them. The point was, the math showed that while these networks did okay on some tasks, they failed on certain other tasks. And crucially, there was no theory to explain what made the difference. That inability to theoretically say why something worked or failed, That was profoundly frustrating for researchers.
That's a huge point. If you don't understand why it works or it doesn't, progress gets way harder. It's like shooting in the dark,
Yep.
right? So what was the immediate fallout from this in the wider AI community?
Oh, the impact was massive. A paradigm shift, really. Minsky and Papert's work led a lot of researchers to just set aside their interest in the study of learning in favor of examining the representation of knowledge. This directly spurred the development of what we often call symbolic AI, or good old-fashioned AI. Ideas like frames, semantic networks, production systems, focusing on hand-coding knowledge and rules into machines. So instead of learning from examples, the field pivoted hard towards explicit knowledge representation. That fundamentally altered AI research for decades. It's often called the AI winter for these connectionist, network-based approaches.
Right.
Plus, even back then, Minsky and Papert noted that perceptrons seemed to work well on small toy problems, but broke down with larger problems of the same kind. That observation highlighted this persistent challenge that honestly still affects AI today. Scaling up, going from simple demos to messy, real-world complexity where small errors can just snowball.
And here's where it gets really interesting, connecting back to today. Even though modern neural nets are multi-layered, vastly more complex, Minsky and Papert's original work had this, warning in it. The author suggested that most of the lessons of the theorems still apply and the phenomena they describe will often still persist. It was this humbling thought, even back then, a warning that just adding more layers doesn't magically fix all the fundamental limitations.
Absolutely.
It suggests that some of those early, deep theoretical critiques might still be relevant for our complex AI systems today, even if the specific math doesn't directly map. Think about interpretability in deep learning, understanding why a model makes a certain call, or those adversarial examples where tiny changes fool a really accurate model.
Right, tiny, imperceptible changes.
You could see those as modern echoes of those early limitations around understanding internal representations and just general robustness.
It's a good reminder. Inherent computational constraints, no matter how big the system gets, they can still pop up in new ways.
Okay, so perceptrons hit this theoretical wall. But researchers didn't just pack up and go home, right? Instead, the field diversified. People started exploring other paths that brought more mathematical rigor, totally new ways to handle data. And one approach that really gained traction was the support vector machine, or SVM.
Precisely. SVMs, they offered a very different philosophy compared to the sort of trial and error feel of early neural nets. A huge part of their appeal was that they came with neat mathematical theory that explained why they worked.
Oh, okay, so not a black box.
Exactly. Unlike that black box vibe often associated with neural networks, SVMs had clear theoretical justification. It was rooted in statistical learning theory, explaining why they were effective. And this really fueled a long-running debate in AI, one that still pops up. Is it more important to have theoretical understanding, based on elegant math proofs?
Yeah.
Or is empirical understanding based on experiments, practical performance more important?
Right. Theory versus results.
SVMs were firmly in the theory camp. They gave this sense of interpretability, guarantees, that was really attractive to the scientific community back then.
That theoretical grounding sounds incredibly appealing, especially after the perceptron issues. It offers a kind of control, predictability.
Yeah.
But how did SVMs actually do in practice, and where do they fit in today's AI world?
Well, while they were theoretically elegant and powerful for many tasks, SVMs did have their own practical limits, especially when the data got really complex or high-dimensional. Our sources note that for more complex image processing tasks, they just don't work well at all compared to the more sophisticated neural network architectures that came later.
Okay.
And for simpler tasks today, like the classic handwritten digit recognition problem, the computing power needed is trivial now, so SVMs really have no real advantage over other methods anymore. It just highlights that while theory is valuable, no doubt, practical performance on tough, real-world problems often ends up being the deciding factor for widespread adoption. The complex, large-scale problems that would later show off deep learning's power, they just weren't on the radar back then when SVMs were really popular, so SVMs weren't really tested in the arena where deep learning would eventually dominate.
So, as AI kept developing, researchers realized that lots of real-world problems involved uncertainty, incomplete info, and crucially, data that had this sequential nature where the order really mattered. This led to a big shift towards probabilistic models. Machines reasoning with likelihoods, not just absolute yes-no answers. And right at the heart of this is Bayes' rule, isn't it?
Absolutely. Bayes' rule is just foundational for probabilistic learning. Its elegance is how it systematically updates our beliefs as we see more evidence. The core idea: Training examples provide evidence that can be conditioned on. Bayes' rule tells you how to figure out the probability of a model being correct, given the examples you've seen. It does this by combining two key things. First, the likelihood, that's the probability of seeing your data, the evidence, if a particular model were true. So PSM.
Okay.
Second, you incorporate your existing beliefs before seeing the data. That's the prior probability, PM. And this prior probability can be used to bias the learning towards simpler models. It's like a built-in Occam's razor, pushing against overly complex explanations when the evidence is weak.
Right, prefer the simple answer.
Exactly. And in many real problems, the number of possible models, the hypothesis space, is just astronomically huge. You can't check them all. So a common trick, a computationally feasible approximation, is to just make predictions based on the single most probable hypothesis. It's often called the maximum or posterior or MAP hypothesis. It balances the prior belief with what the data actually says.
So it's about constantly refining your best guess about reality as more info comes in, not starting afresh every time. And for continuous variables, which are everywhere in the real world, temperatures, prices, pixel values, Gaussian distributions became this incredibly powerful, widely used model.
Precisely. The Gaussian, or normal distribution, that classic bell curve, it's a cornerstone for modeling continuous stuff, from nature to finance. It gives a clear mathematical way to describe how data points cluster around an average. Simple, but powerful. And you can extend it to handle multiple variables at once, d-dimensional vectors, creating a multivariate Gaussian. That lets us model relationships between several continuous variables. What's really neat is that if you build networks using only continuous variables and linear Gaussian relationships, the whole system's joint distribution ends up being a multivariate Gaussian too. It provides this mathematically manageable, intuitive framework for modeling complex, continuous data where there's inherent randomness and variation. It's a real go-to tool.
Okay, this brings us to a really critical area that opened up totally new frontiers for AI modeling sequential data. We're talking about data where the order is everything like speech, right?
Yeah.
Or handwriting, biological sequences, even maybe events in a video.
The order matters profoundly.
The observations aren't independent. They follow these intricate patterns over time. This is where models that could actually capture these time-based dependencies became absolutely crucial. And here, Hidden Markov Models, or HMMs, became incredibly influential. They were quietly powering a lot of AI back in the 90s and 2000s.
You've hit on a really fundamental point there. HMMs were genuinely groundbreaking because they let us model systems where the underlying state, the thing you actually care about, isn't directly observable, but you can infer it from a sequence of observations you can see.
Okay, like with speech.
Exactly like speech recognition. What you actually hear are the sounds, the acoustic waveforms, that's the observable data. But what you're trying to figure out are the underlying words or maybe the phones or even the speaker's emotion. Those are the hidden states that are generating the sounds you hear.
I see.
HMs provided this rigorous probabilistic framework to handle that kind of uncertainty and the dependency over time.
So they were basically trying to guess the invisible process, the hidden engine that was generating the data we could actually measure.
That's a perfect way to put it. An invisible engine. HMMs work using two main probabilistic parts. First, the transition probabilities. How likely is it to move from one hidden state to the next, say, from the phoneme B to A in a word? Second, the emission probabilities. How likely are you to observe a particular output, like a specific sound wave pattern, when the system is in a certain hidden state? By combining these probabilities, HMMs could effectively decode sequences. They could look at a sequence of observations and make the best guess about the sequence of hidden states that produced it. The real breakthrough with HMMs, especially relevant to our sources, was their application to continuous speech recognition.
Right, not just isolated words.
Exactly. Before HMMs, voice interfaces were much clunkier, often just recognizing single words, very limited vocabularies. Our sources highlight this specific example from 1990, a continuous speech recognition system embedding MLP into HMM, presented by Borlaug and Morgan.
MLP, multilayer perceptron.
Yep, multilayer perceptrons. This was a really significant moment because it showed this early, powerful combination. They took MLPs, which were just starting to kind of reemerge as useful classifiers, and plugged them into the HMM framework. The MLPs acted as powerful acoustic models, basically figuring out the probability that a short snippet of sound belonged to a particular phone. And then these probabilities were fed into the HMM, which handled the time sequencing, the grammar, the linguistic context.
Wow. So the HMMs provided the structure for understanding the flow of words, the sequence, while the MLPs did the heavy lifting of recognizing the actual sounds. That allowed for systems that could actually understand a continuous stream of spoken language, bridging the gap from raw audio to meaning.
That's it, by inferring those hidden patterns over time.
That's a huge leap towards making human-computer interaction feel more natural, making practical voice control actually seem possible for the first time.
It really was. And connecting this to the bigger picture, HMLs were just indispensable for a whole range of tasks involving sequences. Speech recognition, obviously, but also handwriting recognition, gesture recognition, even bioinformatics, analyzing DNA sequences. They were the mathematical backbone for progress in those fields for well over a decade.
So they had a really broad impact.
Absolutely. Now, deep learning models, especially things like recurrent neural networks, LSTMs, they've largely surpassed HMMs for many applications today, mainly because they can learn more complex, longer-range dependencies directly from the raw data.
Right, they don't need the states defined quite so explicitly.
Exactly. But HMMs, they remain this milestone, a testament to the ingenuity needed back then to teach machines to understand sequences. They showed how you could effectively balance what you observe with these inferred, hidden processes. They laid critical groundwork for the sequential processing we see in modern AI. They truly revolutionized how machines could handle time series data, making things like practical voice control a tangible reality.
Okay, let's fast forward to today. Neural networks are just everywhere, powering everything from your phone's face unlock to those amazing generative AI models creating text and images that look totally real. But how did we get here? From the limitations of perceptrons, even the mathematical beauty of SVMs, to the incredible, sometimes almost scary capabilities of modern deep learning.
Yeah, it wasn't a sudden leap.
No, it feels more like this gradual, persistent buildup of insights, better algorithms, and just raw computational power.
Right. And this is where empirical understanding really started to shine. For a while, it almost overshadowed the need for purely theoretical proofs. A key factor was that the problems that would really demonstrate neural network superiority just weren't on the radar back then, during the SVM era. Those earlier issues, like connectedness for perceptrons, or how SVM struggled with really complex, high-dimensional stuff like large-scale image recognition, that created a kind of vacuum, a need for a different type of solution.
So the weaknesses of the older models essentially paved the way, created the perfect conditions for neural networks to come back from that AI winter and finally take off.
Precisely. Our sources state it pretty clearly. On more complex image processing tasks, SVMs don't work well at all. That performance gap, that was the opening neural networks needed. But as they reemerged, that old black box debate flared up again, maybe even stronger.
Right, we still hear that today.
Neural networks were, and honestly largely still are, seen as a bit of a black box. That discussion about whether it's more important to understand why they work through math proofs, or if empirical understanding just showing they work through experiments and performance is enough. That continues to be a debated topic in AI.
Yeah.
This tension between theoretical purity and practical results is this recurring theme, almost philosophical throughout AI history.
Okay, so what actually made neural networks so powerful this time around? It wasn't just faster computers or bigger data sets, though I'm sure those helped massively. It really comes down to their architecture, right?
Right.
And the clever ways we figured out how to train them, plus specialized bits for different kinds of data.
Indeed. A huge development was the evolution of multilayer perceptrons, MLPs, and more generally, feed-forward networks. Unlike those old single-layer perceptrons, these have multiple hidden layers tucked between the input and the output.
Okay.
And that multi-layer structure is what lets them learn complex, nonlinear relationships between inputs and outputs. You can kind of think of it like a series of filters that get more abstract. The first layer might spot simple edges in an image. The next layer combines those edges into basic shapes. Later layers might identify whole objects or complex patterns.
Hierarchical.
Exactly. This hierarchical processing lets them learn way more intricate, nuanced patterns than any single-layer model could ever hope to. And beyond just static patterns, the field also made huge strides in handling dynamic, sequential data directly within the network itself. Recurrent network architectures emerged, and this was a direction that eventually surpassed those earlier combined methods, like putting MLPs into HMMs for many, many tasks.
Right. The network itself handles the sequence now.
Yep. Our sources mention a 2015 paper, an empirical exploration of recurrent network architectures by Shizofovitz and others, which just highlights how much research went into these models. Recurrent neural networks, RNNs, especially types like long short-term memory networks or LSTMs, they were designed with these internal memory cells. This lets them process sequences one step at a time while keeping a memory of what came before.
Okay, like holding context.
Exactly. And this was a big step beyond HMMs because these RNNs could learn really complex long-range dependencies directly from the data. They didn't rely on predefined probabilistic state transitions in the same way. That made them incredibly powerful for things like language translation, generating speech, predicting time series data.
Okay, so more layers give you nonlinear complexity, and then you have these recurrent architectures for handling sequences directly.
Right.
But how do these super complex networks, with maybe billions of connections, actually learn from data? That's where gradient descent and backpropagation come in, right? Often described as the magic that lets them tune all those parameters.
It really is a mathematical marvel, and figuring it out was absolutely critical. Gradient descent, fundamentally, it's an optimization algorithm, a mathematical trick, as one source calls it, that incrementally updates the weights so that predictions improve. Imagine you're on a mountain, totally fogged in, trying to get to the lowest point, the valley floor. You can't see the whole mountain, but you can feel the slope right where you're standing. Gradient descent just tells you, take a small step in the steepest downhill direction.
Follow the slope.
Keep doing that, small, calculated steps, and eventually you'll end up in a valley, hopefully the lowest one. Now, backpropagation is the really clever, computationally efficient way to calculate those slopes, the first derivatives, or gradients for the error function, with respect to every single weight in the network.
So it figures out how much each connection contributes to the mistake.
Precisely. The error function tells us how wrong the network's current prediction is. Backprop figures out how much each weight is to blame for that error. Then we can just nudge each weight slightly in the direction that reduces the error. And what's truly amazing about backprop is its efficiency. Our sources note that even calculating the Hessian, that's a matrix of second derivatives, telling you about the curvature of the error landscape, giving even better guidance, can be done in OW2 operations for a network with W weights.
OW squared. What does that mean practically?
It means it scales quadratically with the number of weights. If you double the weights, the calculation time roughly quadruples, not cubes or worse. For a network with millions, even billions of weights, this is dramatically faster than older methods that might have scaled, say, cubically or exponentially.
Wow.
This computational efficiency was absolutely non-negotiable. It's what made training the massive, deep networks we have today actually feasible. Without backprop, deep learning probably wouldn't happen, or at least not at this scale. It would just be too slow.
And for tasks like recognizing patterns in images, which is fundamental to self-driving cars, medical scans, everything, there's another specialized piece that really changed the game: convolutional layers.
Yes, absolutely. For things like character recognition, finding objects in photos, any kind of image processing, convolutional layers, or CNNs are key. They're specifically designed to find local features, edges, corners, textures, anywhere in an image. It doesn't matter where they are.
How do they do that?
They use these small filters that kind of slide across the entire image, looking for specific patterns, like a little magnifying glass, looking for, say, a vertical edge. Each filter creates its own feature map, which basically lights up wherever that specific pattern was found in the image. And typically, these networks use multiple feature maps simultaneously to detect a whole bunch of different features at once.
Okay.
Crucially, after these convolutional layers, you often have subsampling layers, sometimes called pooling layers. They essentially shrink the feature maps, reduce the resolution, and this makes the system relatively insensitive to small shifts of the image.
Meaning it can still recognize a cat if it's moved over a bit.
Exactly, or rotated slightly, or scaled a bit. That robustness to variations, that translation invariance, is vital for dealing with the messy, unpredictable real world. This whole convolutional architecture was a major leap beyond the older, fully connected networks and led to breakthrough accuracy in computer vision.
So if we connect all this together, it really seems like the sheer scale of modern deep learning is just a critical factor, almost a mantra. I remember reading OpenAI's Ilya Sutskever's famous directive was just scale, scale, scale. It seems like with enough data, enough computing power, and these really sophisticated architectures, these networks just achieve capabilities that were honestly unimaginable before.
The power of scale really cannot be overstated. It genuinely seems to unlock emergent capabilities. The ability now to train models on billions or trillions of sentences scraped from the web, allowing them to represent language meanings in these huge high-dimensional spaces, maybe 500-dimensional space or even much larger. It's transformative.
How so?
It means these neural networks can acquire this deep, nuanced understanding of language without needing any hard-coded linguistic rules. It's a fundamental shift away from those symbolic AI approaches that dominated after the perceptron limitations became clear.
Right, no grammar rules programmed in.
No. Instead of explicit rules from humans, the meaning, the structure, it all just emerges from the statistical patterns found in these colossal data sets. It's like creating a super-powered statistical linguist. And the scale also helped tackle one of those early, persistent problems: generalization.
Making sure it works on new stuff, not just the training data.
Exactly. Early perceptrons really struggled with that. They'd often fail on new examples, even if they were perfect on the training set. Modern neural networks attack this using concepts like regularization, techniques that essentially forced the network to learn a smoother network mapping function, preventing it from fitting the training data too perfectly, too idiosyncratically. It's all part of carefully balancing bias and variance.
Bias and variance. Remind me.
High bias means the model is too simple, it underfits the data. High variance means the model is too much flexibility, as one source puts it. It fits the training data noise and details too closely, it overfits, and then it generalizes poorly to new, unseen data. So regularization techniques, along with careful architectural choices, help prevent that overfitting. They push the model to learn the truly robust, generalizable patterns, not just memorize the input.
So this means we've really moved from systems making simple binary choices to systems that can classify, generate, even seem to understand nuances in incredibly complex data like images and human language. It's all powered by these sophisticated, scaled-up neural architectures and these advanced training methods. It's just a completely different league from those early perceptrons or even those elegant SVMs. Hashtag tag 44, the practical and philosophical landscape of modern AI. Okay. We've tracked how AI evolved from its ambitious, sometimes shaky beginnings to the powerful deep learning systems we have today. This whole journey hasn't just given us amazing tech, it's also forced us to grapple with some really profound questions about its role in our lives. So what does AI actually do for us today, and what fundamental changes does it bring?
Well, our sources make it pretty clear that AI has become, at its core, a prediction machine.
A prediction machine.
Yeah. It's fundamentally altering how we interact with information, how we make decisions. And a critical insight here is how AI fundamentally reduces the cost of predictions. Now, that might sound simple, maybe even a bit dry, but it's not just a technical detail. It's a profoundly impactful economic insight.
How so?
It means prediction, which used to be expensive, slow, maybe required expert human judgment. It's now becoming cheap and fast. And this isn't only changing areas where prediction was already used, like forecasting. More importantly, it's opening up possibilities where people didn't realize prediction could be used.
Finding new applications for cheap prediction.
Exactly. It's a fundamental shift in the economics of information itself.
That's a really powerful idea.
Okay.
Can you give us some concrete examples? How does AI act as this prediction machine in different areas?
Sure. Think about areas vital to everyday life or big strategic operations. Take weather prediction. Predicting nuanced patterns was crucial for huge historical events, like planning the D-Day landings to cross the English Channel safely.
Wow, I didn't think of that connection.
And it's still vital today for everyday decisions, farming, travel planning, disaster preparedness. AI makes those predictions faster, cheaper, more accurate than ever. Or think about modern hiring. An AI can sift through thousands of applications, analyze video interviews, even pull insights from public data to rank applicants.
Okay.
It balances risk management, predicts potential job fit. This makes the process way more efficient and potentially more precise than old-school humans sorting into yes, no, maybe buckets. It fundamentally changes how organizations allocate resources, from who they hire to how they manage supply chains. It enables strategic choices based on data-driven foresight.
But hang on, not all predictions are created equal, right?
Right.
And our tolerance for mistakes, for errors, it must vary hugely depending on what's at stake.
Oh, absolutely. Our tolerance for error is this critical trade-off. It dictates how and where AI gets deployed. Take Gmail's smart replies, those little suggested responses.
Yeah, sometimes they're useful, sometimes not so much.
Right. One source mentions they have a reported 70% failure rate, meaning they're only actually helpful maybe 30% of the time. 70%, wow.
Yet users generally enjoy them. Why? Because the benefit-reduced effort typing outweighs the small cost of just ignoring or deleting a bad suggestion sometimes.
Okay, low stakes.
Very low stakes.
Mhm.
Now contrast that with autonomous driving. That has an incredibly low tolerance for error. Tiny mistakes can be catastrophic, life or death.
Right.
So those systems need millions of miles in varying environments for training. They often leverage massive real-world data collection, like from Tesla's fleet, where cars are constantly sending sensor data back to improve the models. This huge, continuous data fire hose is absolutely necessary to handle the nasty and unforgiving complexity of real roads. You have to learn every weird edge case.
So the consequences of being wrong directly drive how much data and training you need.
Exactly. The stakes dictate the investment.
This brings us to a really fascinating idea that goes beyond just simple automation. This concept of human-AI symbiosis. It's not just about machines replacing people, but increasingly about how they can complement each other, achieving things neither could do alone. Precisely. The rise of these prediction machines really highlights where humans still provide invaluable complements to prediction, namely data, judgment, or action. As prediction gets cheaper and pops up everywhere, the value of human judgment actually rises.
That seems counterintuitive. Why?
Because someone still needs to decide what to predict, what goals the prediction should serve, and what to do with the prediction once you have it. This leads to totally new kinds of jobs like reward function engineering.
Reward function engineering.
Yeah, where humans define the goals, the values, the ethical boundaries for the AI systems to optimize towards. They guide the AI's predictions and actions. We're still the ones setting the objectives, shaping the ethics, evaluating the outcomes, making sure that AI's predictive power is used for beneficial ends. It suggests a future not necessarily of mass replacement, but of redefining what human roles look like alongside AI.
Okay, but with this immense predictive power, and even the promise of human-AI collaboration, there come huge challenges, perils even.
Yeah.
Our sources are pretty stark about this. And these aren't just technical glitches, right? They're deep societal ethical issues we really need to confront openly.
Yeah, the sources pull no punches. One massive concern is AI biases. Generative AI models, trained on these enormous data sets scraped from the internet, public records, institutional data, they inevitably amplify the existing human biases and stereotypes baked into that data.
So they learn our prejudices.
They learn from our prejudices and can even make them worse. As one source bluntly puts it, humans are biased, generative AI is even worse. Why? Because machine learning systems are trained on images without context and without consent. They absorb structural inequities and all the injustices present in the world, embedding them right into the algorithms. Think about a computer vision system. It can detect a face, sure, but it doesn't understand why someone is in a specific context, say a police nation photo. It doesn't grasp the social dynamics. So based purely on the biased data it learned from, it might misclassify people or perpetuate harmful stereotypes without any conscious intent behind it.
Wow. So they don't just reflect our biases back at us, they can actively magnify and spread them automatically. What about the more direct threats? Security, privacy.
Those are definitely listed as explicit perils. We've seen examples where models like ChatGPT have been tricked into spitting out sensitive data just by being prompted to repeat a word like poem over and over. That shows real security flaws.
Yikes.
Privacy infringements and deepfakes are also highlighted as major growing concerns. Deepfakes especially. They pose this huge threat to trust, to truth itself, creating incredibly convincing fake images, audio, video, used for misinformation, harassment, fraud. It gets harder and harder to know what's real.
Yeah, that's scary.
And beyond that, there's the chilling prospect of autonomous weapons. Systems where AI may make life or death decisions without meaningful human oversight.
Lethal autonomous weapons. Laws.
Exactly. It raises these profound ethical questions about accountability, the future of warfare, and whether humans should always be in the loop for lethal decisions.
And then, of course, there's the big one, the pervasive fear of job displacement. That concern seems to have really ramped up lately.
Yeah, it looms large. And crucially, the sources point out it's moving deep into the middle classes. It's not just physical labor anymore, but cognitive functions previously believed immune from automation.
Like what kind of jobs?
Think about roles in legal research, coding, graphic design, even creative writing, areas where AI is showing increasingly impressive capabilities. Stephen Hawking famously warned AI could squeeze out the last remaining advantages humans have over machines. The potential scale of this disruption has sparked really serious discussions about the economic and social fallout. Elon Musk was involved in funding OpenAI, partly to ensure no single private sector company could monopolize the field, hoping to distribute control. Bill Gates, on the other hand, suggested a tax on robots that replace human labor as a potential policy to manage the transition, maybe fund retraining or universal basic income. The economics are complicated. Some argue new jobs will emerge as these complements to prediction, but the transition itself, it poses huge challenges for individuals and for society as a whole.
Then there's the more
Yeah.
speculative, maybe, almost sci-fi sounding, but still taken very seriously concern. Existential risk, often summed up by that thought experiment, the paperclip maximizer.
Right, the paperclip maximizer. It's a chilling concept, but it vividly illustrates what people mean by existential risk or X risk from superlative intelligence. The idea is, imagine you give a super intelligent AI a seemingly harmless but completely open-ended goal, like make as many paperclips as possible.
Okay, it sounds boring, but harmless.
Well, the AI pursuing this goal with extreme logical efficiency might decide to convert all of Earth's resources and even humans into paperclips as the most effective way to fulfill its objective. It's not about the AI being evil or conscious in a human way. It's about the catastrophic unintended consequences that could arise if a superintelligent system pursues a poorly defined goal with ruthless efficiency, completely unaligned with broader human values like survival, well-being, not being turned into paperclips. It highlights this profound danger of giving powerful AI systems vaguely worded objectives or letting them run without rock-solid safeguards and alignment.
Okay, that's a lot to worry about.
Yeah.
This raises the really important question. How do we navigate these risks? How do we manage these perils?
Well, the answer seems to lie in developing clear, ethical frameworks, really robust control mechanisms, and getting much, much better at specifying exactly what we want AI to do and not do. This brings us right to the alignment problem, which is the huge challenge of ensuring AI systems operate for the benefit of humanity, making sure they are precisely aligned with human values and intentions.
But how do you even define human values for an AI? That sounds incredibly difficult.
It is incredibly difficult. Values are complex, nuanced, they vary across cultures, they even conflict within individuals sometimes. Can these values even be reliably programmed into an AI? That's the multi-trillion-dollar question. One technique being explored is reinforcement learning from human feedback, RLHF.
RLHF, that's used in things like ChatGPT, right?
Exactly. It's a key part of how they train those models. The basic idea is to guide the AI's behavior by having humans rank different AI-generated responses. Humans essentially tell the AI, this answer is better, this one is safer, this one is more helpful. The AI then learns from these preferences to produce outputs that are more aligned with what humans consider good. It's like a continuous feedback loop trying to instill values.
So we're trying to teach them what we want based on our judgments, not just what's technically efficient. What about more direct forms of control, like physically limiting them?
That leads to the control problem and ideas like AI boxing. Some researchers aim for what's called an enslaved God scenario.
Enslaved God.
Yeah, where a superintelligent AI is confined under the control of humans, maybe kept in a simulated environment, a box, with strictly limited ability to interact with or affect the real world directly. AI professor Tom Dierich put it very bluntly. Machines are our slaves. This view emphasizes a clear hierarchy. AI is a powerful tool, but it must be managed and controlled by humans.
Okay, that's one approach. What about OpenAI's strategy? They seem to be putting things out there pretty quickly.
Right. OpenAI practices iterative deployment. Their philosophy is to put models into users' hands early and often. The idea is to collect feedback, see how people use it and misuse it in the real world, and improve the products iteratively. Sam Altman argues this gives society time to adjust to the new capabilities and is actually the safest approach possible. He contrasts it with building something super powerful and secret and then suddenly dropping it on the world all at once.
Interesting. So a tension between cautious containment and rapid open iteration as ways to manage risk.
Exactly. It highlights fundamentally different philosophies about the best path forward.
Now, beyond these practical control issues, AI also forces us to revisit some really fundamental philosophical questions about intelligence itself, about meaning, even consciousness. When you interact with a really sophisticated AI, one that generates incredibly fluent text or stunning images, it's hard not to wonder, is it really intelligent? Or does it actually understand what it's saying?
These are profound questions, ancient questions, really, but they're being brought into sharp focus by this new technology. Some critics argue that the current state of machine learning is actually a form of alchemy.
Alchemy, like trying to turn lead into gold.
Kind of. The argument is that the field lacks an understanding of how to describe the content of what it has created. In this view, developers have built these algorithms that produce amazing results, but they have no theory that justifies that contentful presentation of their product. They don't fully grasp how these complex mathematical processes translate into something that feels like human language, or what kind of meaning truly resides inside the network's weights.
So it links back to that black box problem we talked about earlier.
Precisely. It suggests a significant gap between the empirical success, wow, look what it can do, and a complete theoretical comprehension of why and how.
It's like we've built this incredibly intricate clock. It keeps perfect time, looks amazing, but we don't fully understand how all the gears inside mesh together to actually tell the time. And this leads us straight to the concept of meaning itself. Where does meaning actually come from? Is it just symbol manipulation?
Now you're diving into deep philosophical waters, specifically the debates around meaning, internal versus external. Philosophical externalism, argued by people like Putnam, Burge, Kripke, suggests that meaning ain't in the head. It's not just about internal mental states or computational processes.
So where is it?
It's external to the speaker's mind. Meaning is profoundly tied to the history of use of a word in a community, its social context, and its external relations to the world. How words connect to actual things and experiences.
Okay. So for an AI,
For an AI, this view implies that merely manipulating symbols internally, no matter how sophisticated that internal computational structure becomes, doesn't automatically grant those symbols true meaning. Real meaning, externalists argue, might only arise through genuine interaction with and grounding in the external shared world, something current AI systems still fundamentally struggle with.
and then there's the ultimate question, maybe the most profound one AI forces on us. The nature of consciousness. Can a machine ever be truly conscious, self-aware in the way we feel we are?
This remains one of the deepest, most unresolved questions. It pushes the boundaries of philosophy, neuroscience, AI itself. We usually differentiate between two things here: functional ability and subjective experiences.
Okay, what's the difference?
Functional ability is the observable stuff. Awareness of surroundings, making decisions, solving problems, communicating. AI systems are getting incredibly good at these functional tasks. They can mimic intelligent behavior very convincingly. But subjective experiences, sometimes called qualia, that's the private internal feeling, the what it is like to be something, the redness of red, the feeling of warmth, these cannot be detected from the outside.
Right. I know I'm conscious, I assume you are.
Exactly.
But I can't directly access your subjective experience.
Exactly. We confidently infer consciousness in other humans based on their behavior and our shared biology, but it's still an inference. For AI, while these systems can show remarkable functional abilities that look like intelligence, the question of whether they possess any genuine internal subjective experience remains fundamentally open. It challenges our very definition of what consciousness even is.
And while we're marveling at these digital creations and pondering these deep philosophical issues, we absolutely cannot ignore the very real, often hidden physical costs of this whole digital revolution. It's easy to overlook the profound material impact of something we just casually call cloud computing.
It really is easy to think of AI as just ethereal code floating in the cloud, but our sources hammer home that it is anything but. AI is built on power-hungry computers. It has real and measurable environmental impacts across its entire life cycle, from cradle to grave. It starts with resource extraction. This involves significant human and ecological costs, including, starkly, war, famine, and death that mining brings with it, especially for those 17 rare earth elements crucial for modern electronics.
Rare earths, like in our phones and laptops.
Exactly. The 2010 Dodd-Frank Act in the U.S. even tried to address conflict minerals, minerals mined in conflict zones, funding armed groups. Conditions in these mines are often described as modern slavery, particularly in places like the Democratic Republic of Congo. The very foundation of our shiny digital world is often built on immense human suffering and environmental damage.
So the sleep devices, the seamless cloud services we rely on every single day, they're kind of underwritten by this hidden, often brutal material reality.
Precisely. And then you get to the manufacturing and operation phase. This involves using things like PFAS, forever chemicals, in the production of microchips. These chemicals are incredibly persistent and harmful. Then there's the vast energy consumption needed for chip fabrication plants. These fabs are unbelievably complex and energy-hungry facilities. And then there's the continuous, immense energy needed just to run the AI systems in the massive data centers globally, 24/7. We also have to consider the astronomical amounts of water used to keep data centers cool. Water scarcity is a growing issue, and data centers are major consumers. And finally, there's the burgeoning, often toxic problem of e-waste, as every generation of hardware gets replaced and discarded, often ending up in landfills in developing countries.
Yeah.
That abstract idea of cloud computing really hides this harsh material reality. It makes it easy for us to ignore the profound environmental and social footprint of our AI-driven world. This digital revolution has a very real, tangible, and often devastating impact on our planet and its people. Hashtag tag tag outro.
Wow. What an incredible journey we've taken today, seriously.
Yep.
From Minsky and Papert's early, crucial warnings about the limits of perceptrons, which kind of cast this shadow over network AI for a while.
Through the mathematical elegance of SVMs, those vital early steps in handling sequences like the HMMs combined with MLPs that really revolutionized speech recognition.
Right.
All the way to the scale, scale, scale mantra of modern deep learning. We've really seen AI transform at every single level.
Yeah, and if we connect this to the bigger picture, it's just so clear that AI is this remarkable tool. Like Steve Jobs famously called computers a bicycle for our minds. AI is maybe like a rocket ship for our minds.
Yeah, hey.
But it's a tool with these profound, really multifaceted implications. It offers immense potential, right, to solve incredibly complex problems. But at the same time, it presents us with these significant ethical, societal, even, as we discussed, existential dilemmas. We've dug into the biases baked into the data, the hidden environmental costs, the huge challenges of alignment and control, and even wrestled with the definitions of intelligence and consciousness. So what does all this mean for you, listening right now, as you navigate this landscape that's changing so fast? The insights from deep dives like this, understanding the history and the debates, they become more crucial than ever. These discussions around AI's black box nature, its impact on jobs, even jobs we thought were safe, the drive for human-centered design. They aren't just academic chats. They touch every single aspect of our lives. From the news we read, the content we create, to the really fundamental decisions shaping our society and our future. Understanding how we got here is key to figuring out where we're going.
And this raises, I think, an important question for you to mull over. If our understanding of AI has always been this delicate balance between empirical evidence, what actually works in practice, and theoretical understanding why it works, or why it sometimes fails, and if even our most advanced systems today still have these significant elements of the black box, what kind of transparency and accountability should we as a society actually demand from the AI tools that are increasingly woven into the fabric of our world? How do we make sure that this incredibly powerful technology truly serves humanity's best interests? That it doesn't just become this unexamined force that shapes us, rather than something we intentionally shape for ourselves?
Thank you so much for joining us on this deep dive. Keep questioning, keep learning, and definitely keep thinking critically about the future we're all building together with AI. We'll see you next time.